Good morning, everyone. My name is Xavier Besseron from the University of Luxembourg. I'm a research scientist in the XDEM Research Center, and today I'm going to present you our work on the parallel coupling strategy for multiphysics applications in the extended discrete element method. So first, I'm going to introduce what is XDEM, the extended discrete element method, and give a few words on what is multiphysics coupling. Then I will go more into details about the CFD-DEM parallel coupling that we use in XDEM, and in particular, I will detail our two approaches, the collocated partitioning strategy and the dual-grade multiscale approach. Then I'm going to present some result and performance evaluation before concluding. What is XDEM? XDEM stands for Extended Discrete Element Method. So the DEM is a classical simulation approach that typically simulates the particle dynamics, simulates the particle motion by calculating the impact forces and torques. This method has been extended with particle conversion, which means that we simulate heat and mass transfer and chemical reaction within the particle and in between the particles. Additionally, XDEM is can be coupled with external libraries for CFD or finite element method. For example, for CFD, we are able to couple with OpenFOAM or ANSYS Fluent, and for finite element method, we're using DIFPAC, Build2, or Calculate. Here are some examples of applications that we are running with XDEM. So those applications here are pure DEM applications. For example, on the left, we can simulate the brittle failure of some material. Due to the load and the pressure on top of the column of particles, they will break and following the brittle pattern in this case. On the right, we have an example of a Hopper charge and discharge. So here we have about 1 million particles of different sizes, and we can see how they behave while they are being dropped into a hopper. And we can, for example, analyze how the small particle will get stuck in some particular part of the hopper. Here, another type of application. Here, application coupled with FEM. On the left, we have the deformation of a tire while it's rolling on the ground. So in that case, the particle motion are simulated with XDEM, while the deformation of the tire is simulated with an external library coupled with XDEM. In that case, it is DIFPAC. On the right, we have another example of particles falling onto an elastic membrane. This case helps to more visualize the deformation of the membrane over the weight of the particle. As a third example of application, here we have the application of XDEM coupled with CFD. Those are the applications we will be more interested in for the talk of today. And here I show you 3 types of applications. So on the left, the first application is the production of iron and slag within a blast furnace. So blast furnace is this big furnace at the bottom left that is used to produce steel. In the middle, we simulate the wood combustion inside a biomass furnace. So what happens in that case is that the wood particles are rolling at the bottom of the furnace from the right to the left, and there will be a combustion of the wood that will be transformed to char and ashes. The gas flow, hot gas flow, will make the combustion of the particle possible, and also there will be a production of CO and CO2 that we can analyze thanks to the simulation. On the right, we have another example of simulation coupled with CFD, which is coming from the field of additive manufacturing. So in that case, there is a laser which is melting the metal particle to draw or to cut a part of the metal, and this metal is melting. and the liquid metal is then handled by the CFD software. So now a few words on multiphasic coupling. So multiphasic coupling is actually quite a complex field because it involves a lot of multiphysics software and numerical methods. As an example, the one we are dealing with within XDEM are, for example, the computational fluid dynamics, the finite element, or the discrete element method. And what we are trying to do is instead of using a monolithic software, to use different libraries, so well-capable libraries. So, for example, we're coupling XDEM together with OpenFOAM. The problem with multiphasic coupling is that you will have to handle different meshes and different mesh topology, but also different numerical methods that each of them have different constraints in terms of time step, of convergence. And additionally to all that, you have technical constraints. So every software has a different coupling API when they have one. That's different way for communication or data exchanges. They scale differently on different constraints. And of course, you still have the physics constraint of the problem that you want to respect. So for example, you want to conserve mass and energy, but you also want some value to be consistent while you will interpolate some value from one mesh to another. So the conclusion of that is that when you have a complicated physics, it will create a complex software, and then in the end, to get good performance is quite a complicated task. So let's look at a more concrete example. So in the case you want to couple a fluid flow here at the top left, and together with a deformable flap that will be handled by FEM, what you will get is a coupled surface, because the fluid will not go within the flap, and we are only interested about the force applying on the flap and the displacement of the flap. So the data that you need to exchange between the fluid flow and the deformable flap correspond to the surface of this flap, which in the end, that's why we have a surface coupling. This is a typical case of fluid structure interaction, or called FSI. But another type of coupling will be a volume coupling. So let's consider you still have the same fluid flow, but now you have particles that you want to put within this fluid. And now we have much different coupling pattern, because we realize that the particles, they are completely within the fluid, and they can move anywhere within the fluid. So in that case, what we want to couple is a volume, which will make the amount of data that we have to exchange much bigger, because it will correspond to the full volume of the fluid, where all the particles they can move.
Let's now focus on a more specific case of the CFD-DEM volume coupling. So for CFD-DEM coupling, what we want to simulate is particle moving, interacting with liquid or gas. So the particles are immersed within the liquid or the gas. To do that, what we want to exchange from the CFD to the DEM, we want to exchange the lift force, the buoyancy, that will lift the light particle and let the heavy one fall, and the drag force, let's say the force coming from the fluid moving, pushing the particle. On the other way, from DEM to CFD, we want to take into account the effect of the porosity over the fluid. For example, when there are a lot of particles, it will prevent the fluid to move, so this will decrease the porosity. And we want also to take into account the effect of the particle momentum, particle moving, that will actually push the fluid. We can also do some other coupling, exchange other type of value between CFD and XDEM, for example, heat and mass transfer, but we will not consider that for now. So what are the challenges of parallel coupling between CFD and DEM? The first challenge is that we want to couple two independent softwares that were not designed to work together initially. The other problem that I have highlighted earlier is that it is a volume coupling. Because the particles are immersed within the fluid, we have to exchange the volume of the domain where the particle and the fluid can be together, which represent a 3D volume, which corresponds to a large amount of data. Additionally, there will be a different distribution of the computation and of the data in CFD and DEM. Another problem is that the particles are moving, the DEM particle, which makes like the data distribution is dynamic and will change over the simulation. Finally, we have different type of meshes between the CFD and the DEM domain, so we will need to do some interpolation. In the classical approach, in the literature, to do CFD-DEM coupling, the approach used was to have each software being partitioned independently and then exchange the data between the CFD and the DEM in a kind of peer-to-peer model. So let's go a bit more in detail about what happened. So we have two domains overlapping. One is a CFD domain for the fluid, and another domain is a DEM domain with the particles. The two domains overlap in space. Now let's look at them separately and consider the classical approach. In the classical approach, the two domains are partitioned independently. So the CFD domain will be partitioned in that way, and the DEM domain will be partitioned in the other way. Now, if you want to do all the data exchange necessary for this coupling, you see you will have a very complex pattern. Also, that will be an unpredictable pattern, because you don't make any assumption while doing the partitioning of one domain or the other domain. So what we propose to address this issue is a collocated partitioning strategy. So what we will impose is that the domain elements between the two domains will be collocated according to their location in space, and we will ensure they are assigned to the same partition. Thanks to this collocation, we can have some more clever communication strategy. Here on the left you see the processes for the open form, so the CFD part, and on the right the processes, the partition for the XDEM part. And we ensure they are collocated, meaning like the two partitions from for rank 1, they will be actually running inside the same process on the same node. And same for the second partition and the third partition and the fourth partition. And then we can highlight different type of communications that will occur between the processes and between the physics module. So first there will be the intraphysics data exchange. Those are the communications, the data exchange between the partition but within the same physics module, so within XDEM or within OpenFOAM. We let this communication happen natively using the native implementation of each software. The other type of communication will be the intrapartition interphysics data exchange. So those are the communications that happen between the two physics software, but for the partitions that are collocated. So because we ensure that the two partitions are assigned to the same process, by linking the two executables, the two libraries into one executable, then this data exchange can be done actually by direct memory access, and then they will be much faster than traditional communication using a network interface. And finally, the third type of communication will be the interphysic, interpartition data exchange. And those partitions will have to be implemented, for example, using an MPI communication layer. But the idea will be to reduce them to a minimum, because depending on how you have partitioned your domain, actually you can make them null, so no need to do this communication at all. So now let's have a look at the second approach that we use to handle CFD-DEM coupling within XDEM. So this is a dual grid multiscale approach. So the idea is to consider first a bulk coupling scale for the software and a fine scale. So you have a coarse grid on one side and a fine grid on the other side. And the fine grid will be used on the CFD side to solve the fluid in a fine scale in a very precise manner. But on the top side, for the DEM part, we will use a coarse mesh. And the coarse mesh will have the advantage that it will average the physical property from the fine mesh and bring them to the coarse level of particles. So what it will do on one side, it will take the properties, the physical properties of the particles that are much coarser, and allow them to bring them to the fine mesh, where they can be solved at the right precision using the CFD method. And the other side, for example, the fluid velocity calculated on the fine mesh will be interpolated into the coarse mesh and will give an average value that can be applied to the whole particle. So this has the advantage to keep the good volume average property on the DEM side, but still, thanks to the fine mesh, it will give the great convergence. So now our thing within XDEM is to combine those two approaches together. And what we can do is that we will use together the dual grid and the collocated. And so this means that we will have two grids into the system. So what we will do, we add in the middle this coarse mesh that will be an intermediate layer between the CFD and the DEM. Thanks to that, we avoid any constraint and alignment constraints that are required for the collocated approach. Between the coarse mesh and the fine mesh, we will do an interpolation of the physical value and the communication. But on the coarse mesh, we have perfectly aligned partitions between the coarse mesh and the DEM, which means we can completely avoid the interphysic communication at that layer. Let's have a look at the validation of the result. So first, to validate the result, we will build a simple example, a very simple benchmark. So for this one, we will take one single particle in a rectangular domain that will be accelerated by the fluid moving from the left to the right. And we will distribute will partition this domain and put the two parts of the domain, the left and the right, on two different processes. And we will measure and see the result of the simulation. The graph on the left corresponds to the CFD side, and we check the part of the solid volume within the CFD and the fluid acceleration, how they evolve over the time, and in particular when the particle cross the process boundary. On the right, we have on that side the particle velocity and the particle acceleration for the DEM part. And same thing, we're going to see the value while the particle is moving across the process boundary. And one we can notice is that the drag force and the particle velocity, they are continuous, and also that the results are completely identical between the sequential and parallel execution. Another validation example, we take this classical example from the literature, which is the dam break example. So the dam break is about a column of water, and we inject within this column some particle, and we let it fall. And what we're going to be interested in that case is the liquid front, which means the position of the first part of the water. And we're going to compare the result of the position of this liquid front over the time between sequential execution, parallel execution, and we will also compare it with experimental data. So this is the result of the execution, and we can see that first we have no difference at all between the sequential and parallel execution, and also our result match pretty well with the experimental measurement. Now let's focus on the performance evaluation. First, we're going to do some scalability result on the collocated approach only. So we build an artificial benchmark which corresponds to this box made of 10 million particles and 1 million CFD cells, and we make sure that the CFD mesh and the DEM grid are perfectly aligned. The particles are distributed uniformly within the whole CFD domain, and then we're going to measure the scalability from 1 to 10 nodes. In that case, we have 28 cores on each node. And so with this simulation, first we have measured a computational load where we spend like 92% of the time within XDEM, because we have a lot of particles, and only 8% of the time within OpenFOAM. And then the amount of time spent to do the interphysic data exchange is only 0.1% of the time. This is the scalability result. So we can foresee with a green line that so OpenFOAM does not scale well in that case. This is normal because in that case OpenFOAM is a bit underloaded for this number of nodes with less than 4,000 CFD cells. XDEM scale well, and we can see that in purple this is the line for the coupled solution, and we can see that the trend of this line follows actually the dominant part of the code, which in that case XDEM. So the scalability result in that experiment is, I would say, is pretty good. Now we're gonna try a weak scalability experiment with the goal to measure the communication overhead. So we're gonna take a box which is very similar to the one we have used previously, and we're gonna run it on 10 nodes, and then on 20 nodes, and then 40 nodes, and every time we will increase the size, so the size of the domain, which means the number of CFD cells and the number of particles. For this experiment, we use our Bosch approach combined, the collocated partitioning and the dual grid approach. And same as before, the particles are uniformly distributed over the CFD domain. So this is the result of the experiment. So when we increase the number of nodes from 10 to 20 to 40, this is the total number of core processes. Here we use one process per core. So we go from 280 to 1120. And we measure the average time to simulate one time step. While the amount of work of computation, which means the number of particles, the number of CFD cells, this number is constant, is the same per core. The increase in the average time is due to the overhead, due to the communication. And what we measure here is that the overhead is very low. When we double the number of core, we have plus 1% of overhead, and when we go from 10 nodes to 40 nodes, we have 2.3% of overhead. If we compare to the other solution from the literature, or the solution doing CFD-DEM, of course on similar configuration, we can see in their case an overhead of 160% or 50%. This is due to the problem we have highlighted earlier, that in that case they do process-to-process communication because they don't do any collocation approach to minimize the communication. Now let's have a look at a more realistic test case, and here we're going to take a dam break again, but a bit bigger. And so in this setup we have a column of water, and we will have two layers of particle. A layer of heavy particle, which are at the top of the column of water, and a layer of light particles that will be at the bottom. So what will happen when the simulation will start, the column of water will collapse and go to the right, and the heavy particle will fall to the bottom of the box, and the light particle will go to the top. So for this simulation, we can see an overview of the different grids that we use. So we have the very fine grid that is used to solve the CFD, so the fluid in red. We have the coarse grid, which is used as an intermediate layer between the CFD and DEM, and this grid is in green. And there is the DEM cells that are used to locate the particle, which is the same as the coarse grid of the CFD. And now we will run the scalability test from 4 nodes to 78 nodes. So this is the result of the simulation, the speed up, and so it scales quite well until 100 2050, and after the efficiency is a bit lower, but still above 2000 core, we have an efficiency of 63%, which is still quite good for the complexity of this combination of software. So this is the output of the simulation with rendering. So this is what it looks like. So in that case, there was like 10 million CFD cells and a bit more than 2 million particles. So as a summary, we have presented the parallel coupling approach that we use for our coupled CFD-DEM simulation. So we leverage two ideas. First idea is a collocated partitioning. So the goal is to enforce a partitioning between the two software to make sure that partition between the two domains that are collocated, that are close in space, will be collocated on the same process. Of course, to get this to work, it imposes some constraint on the partitioning and some alignment constraint between the grid, between the mesh in CFD and DEM. But the second idea is to use a dual grid multiscale. And this one has many advantages. First, it improves the convergence of the CFD part because we don't have any constraint coming from the DEM regarding the mesh. So the CFD part is free to have any mesh that better suits the CFD problem. And there is this intermediate coarse mesh that will better suit the DEM part. And the other advantages of this approach is then, because we are free to choose the coarse mesh the way we want, it will relax the alignment constraints that we need on the CFD side. The next step to move forward in XDEM is actually to add the support for the heat and mass transfer with this approach dual grid plus collocated, because right now it has only been implemented for momentum transfer. So the issue for that is we have to ensure the energy and mass conservation while we do the interpolation between the two meshes. There are still a lot of open issues to get a good performance for parallel coupling and parallel volume coupling. So what is actually really needed and what is highlighted by this collocated partitioning is that there is a need for a multi-physics aware partitioner. Because there is an unequal load distribution between the different software, because there is a different data distribution between the two software, and also because the amount of data to communicate can be important, in particular in the case of volume coupling. Also, another problem that comes with DEM in particular is that the load distribution will change over the time, because the particles will move. So they will move from one part of the domain to another, which will completely change the distribution load and the computation load and also the communication load. So this is something to be taken into account by such multi-physics aware partitioner. Which means that we have to do some dynamic load balancing and repartitioning, and then that's something that has to be applied to each of the software, included taking part in this coupling. Then we are dependent of the capability of this software. Then there are some constraints to be resolved on the mesh, because of course we have to do some interpolation, and maybe interpolation of arbitrary meshes that come from different software. And there is a need to do a proper implementation of this interpartition and interphysics communication, but maybe also in the case of moving mesh. So to solve such issue, actually, we are looking toward using a generic coupling framework, like, for example, Precise or on OpenPalm. They would solve a lot of issues, but also they will bring some more constraint, and for example, they will make it difficult to use this collocated approach where we link the two libraries within the same executable. I'd like to thank you for your attention. Some result of this presentation has been published in this journal article available here, and I will be available after the talk for any questions that you might have. Thank you very much.